طيب بسم الله الرحمن الرحيم. We're still talking about the distant vector routing protocols, and we have, as we have discussed before, we mentioned two examples of distant vector routing protocols that we will study in details. One is the routing information protocol, or RIP, and the other one is EIGRP, or extended interior gateway routing protocol. So we'll compare again the features of each of these two routing protocols quickly. And this is not a complete list of features. We will talk about other features of REP. So REP, based on what we have discussed before in terms of eliminating the routing loops, REP uses split horizon and split horizon with Poisson reverse to get rid of the routing loops. REP is also capable of load balancing. So all these are mechanisms and concepts that we have discussed before. REP is easy to configure in terms of the fact that, as we said, REP has a very simple implementation based on the distance and the direction of the vector, and because of the simplicity of the implementation, it's very easy to configure, and it works in multi-vendor router environment, which means that REP is actually a standardized protocol. So we all know that the standard means that any vendor who implements this standard, their device will be able to communicate with any other device which is manufactured by any other vendor. So this is the basic meaning of standard. Standard means that if it's implemented in any device, it will be able to communicate with other devices which are manufactured by other vendors. So these are the basic, and of course there are some specific features, like we said, that REP uses hop count as a metric. REP uses periodic updates using a period of 30 seconds by default, 30 seconds for updates. So these are some others. On the other side, EIGRP uses triggered updates. Okay, so REP uses periodic updates every 30 seconds. EIGRP uses triggered updates. So as we said, trigger updates means that only if there is a network change, we form a route update and we send it in a broadcast fashion. Actually, not in a broadcast fashion, because it's partial and it's bounded. Because of the fact that EIGRP uses triggered updates, EIGRP also uses what we call a hello protocol to establish neighbor adjacencies. What does that mean? This means that in any network, when the router first starts and you start EIGRP, EIGRP functions in two separate steps. Okay, in two separate steps. The first thing that any router does, it will have to send hello packets to all the neighboring routers in order to discover the topology. Why? Because of the fact that EIGRP uses, as we said, partial and bounded updates. So I need to know which router I should send this update to. In order for me to do this partial update and bounded update, I have to discover who the neighbors are first. REP didn't have to do that. Why? Because REP does not use partial updates. You see what I mean? Because of the fact that REP does not use partial updates, any update is actually a broadcast. And the update is unreliable, as we will see in a minute. The update is unreliable, and I don't care if there's no scenario based on which the REP router will send the update to specific routers. There's no such thing. But because for EIGRP, it uses partial updates, in which case I send the update to specific router. So first I have to discover who the neighbors are in order for me to target a specific router. So in other words, EIGRP discovers the topology of the network, not globally, but locally, because we said that only for link state routing protocols like OSPF, we have to construct, or we have to know the global topology of the network. EIGRP tries to discover the neighboring topology of the network. Okay. As we will see in a minute, RIP uses classful. RIP is a classful routing protocol, and we will see what that means. EIGRP on the other side uses VLSM, variable length subnet mask, which indicates that it uses classless addressing, which means that the route updates for EIGRP, they contain subnet masks. So I have to communicate the subnet masks back and forth between the routers. In the case of REP, we don't have to do that. We don't actually send any subnet mask as part of the routing update. Okay? EIGRP use the use of topology table to maintain all routes, and this combines with the Hello protocol. So through the Hello protocol, you discover the topology, and you have to maintain that topology in a topology table in order for you to send targeted updates to targeted routers, because the updates again are partial and are bounded. Okay, so in order for EIGRP to do that, it has to maintain the topology table. I forgot to say that EIGRP also uses route summarization, and we will see that RIP also uses route summarization as well. So this is not a distinction for EIGRP only, but this one is not supported by RIP in terms of sending the subnet mask as part of the route update. EIGRP is a classless distant vector routing protocol, which means that EIGRP sends the subnet mask as part of the route update. And listen carefully to the definition, because the definition is very accurate. Classless distant vector routing protocol means that the route update will contain the subnet mask. Okay? REP is a classful routing protocol, in which case REP does not send subnet mask as part of the route update. And this is an accurate definition, because that doesn't necessarily mean that REP does not deal at all with classless addresses. We'll see that in a minute. EIGRP is a proprietary protocol. What does that mean? Does anyone know what proprietary means as opposed to a standard protocol? Anything? So proprietary means that this has been implemented by Cisco internally, and there's no specific standard or RFC. You know RFC from this is the standard specification. Okay, the standard specification, it gets published publicly to all the vendors, to all the manufacturers. Okay, and then the manufacturers will get the standard specifications and they try to implement it in their devices. If they do that, if all manufacturers implement the same specifications on their devices will be able to talk to each other, which means that now this protocol or this technique is a standard. It's publicly available. EIGRP on the other side is proprietary. This is the reverse, or this is the opposite of standard, which means that it's only specified or defined in terms of specification internally within Cisco, but there's no specific RFC or standard specification for EIGRP which is publicly available. So with that said, why EIGRP is widely available? Because of the fact that the Cisco routers are widely available, because Cisco routers, they constitute more than 95% of all routers worldwide. And that's why EIGRP is very widely available in all the Cisco routers. Okay? And chances are, since Cisco routers constitute 95%, they can talk to each other. Of course, Cisco routers, they can talk to each other. And EIGRP in that case can be used seamlessly between the routers.
So it can be implemented only on Cisco routers, right?
Yes, this is what proprietary means. There's no restriction for EIGRP to be implemented on other brand routers. But again, that doesn't mean it's a standard, because standard means that it's publicly available worldwide. Okay? So that's what proprietary protocol means. And of course, Cisco is pushing EIGRP as what they call a de facto standard. It's a de facto standard because it's very widely available, although there is no standard specification for it, but it's very widely available. So starting from here, we will start digging and discussing RIP version 1. And these are the high-level objectives. Of course, just a quick historical note. RIP version 1 has been standardized, which means that the RFC for RIP version 1 has been released in 1988, around that time, late 80s, okay? And later, like 6 or 7 years after, they released RIP version 2. So we will see the difference between RIP version 2 compared to RIP version 1 as part of this discussion. And then maybe like 3 or 4 years after, they have released what they call RIP next generation, which is for IP version 6. So for IP version 6, you have to redesign all the routing protocols and everything. All the protocols that you have learned in 455, they have to be redesigned completely for IP version 6. And RIP next generation is the standard for IP version 6. But we're not going to discuss IP version 6 as part of this course, and we'll focus on RIP version 1, and then we will study the differences for RIP version 2. So the high-level objectives of that part is to describe the functions and the characteristics of IP version 1 protocol, to describe how RIP version 1 performs the automatic summarization, so we'll know what automatic summarization means and how it works, and what are the recommended techniques to solve problems related to RIP version 1, like for example, to solve the problem of routing loops, what are the techniques that RIP version 1 supports. Okay. So again, in terms of high-level characteristics for RIP version 1, it's a classful distant vector routing protocol, which means, again, the definition, and you have to be accurate in defining what classful routing protocol means, that RIP does not use or does not include subnet masks as part of the routing update. Okay? That doesn't mean that routing tables will not have a subnet mask. That doesn't mean that the RIP routing protocol does not deal at all with classless addresses. I didn't say that. But the definition is it does not send subnet mask as part of the route update. Okay? So the metric for RIP is simply the hop count. And as we said, there are some other possible metrics that we have studied, including bandwidth, including delay, including the load and reliability, and so on. But RIP uses simply the hop count. And as we have discussed before, the hop count more than 15, for us this is infinity. If the hop count is 16 or more, this means that this network is unreachable. This is what we have discussed as part of routing loops, that we said that the route update will keep incrementing the hop count until it reaches 16, which indicates that this network is unreachable. And it uses by default route updates every 30 seconds. So every 30 seconds, the router will gather the information in the routing table and will send it in a broadcast fashion to all routers around it. Okay, any questions so far? So we'll dig into the message specification for REP version 1. So the message here for REP version 1, the message represents the route update basically. Okay, and this message contains the information from the routing table. So the first thing we notice here is that the message contains data link layer header, it contains IP packet header, and it contains UDP, which means that the route update, they get encapsulated using UDP transport layer protocol. So this is the first thing we notice, which means that route updates are reliable or unreliable? Unreliable. Okay? Which means that the route updates, they get sent in unreliable fashion. The other thing is that the maximum length of the REP version 1 payload, the payload only, is 512. Okay, so based on the format, you notice that based on this format, you notice that 512 can contain up to 25 route entries. Okay, so 25 route entries will be encapsulated or incorporated into a payload with a length of 512 bytes. UDP is unreliable, right? So, which means that when you send the route update, it may actually not reach the other router. So what does that mean? Conversions will be slower. As simple as that. Okay. So you have up to 25 route entries. So what happens if the routing table has more than 25 entries? Well, you will have to send the update using multiple messages. Okay? So if you have like 50, you have to send 2 route updates back to back. Okay? But the maximum number of route entries you can incorporate in this message is 25. Okay, kid? Type. Let's go into the details of this message format. We notice that you have basically 2 things. You have the rep header, and then you have the route entry. So you have the rep header and the route entry. The rep header is this one, the orange part, and the route entry is this one, the blue part. Okay, so the rep header simply contains 3 fields: the command field, which we will talk about in a minute, version field. What does that indicate? This indicates whether this is rep version 1 and rep version 2. Why do you have to communicate the version as part of the update? Why do we have to do that? Huh? Because both have different features. That this is correct. And for example, some routers may not support Rev version 2. So if they receive route update for Rev version 2, they ignore it because they cannot really understand what that means. Okay, so you always try to be backward compatible. In which case, if you have a support for Rev version 2 and you receive route update for Rev version 1, will you be able to recognize what that is? Yes, because you are backward compatible, right? But the other way around is not possible. So if you support only Rev version 1 and you receive a route update for Rev version 2, you're puzzled. You don't understand what that means. Okay? So always the more recent versions of any protocol, they are, not always, but in most of the time, is backward compatible. Okay? Okay, so so there are 3 fields, but two of them actually, they contain some information. The third one is simply must be 0. Must be 0 here means that it's left blank and it has to be 0, okay? But it does not indicate any information. And this is sometimes is done as part of the protocol specification to plan for future releases or to plan for future updates to that protocol. Okay? The route entry part, which is the blue part here, it contains again 3 different fields. The address family identifier, and here it indicates whether this is like IP address or IPX or any other routing or any other network level protocol. Okay, so for IP, simply the value is 2. So for IP, the value is 2. So 99.999% of the time, this field will contain simply a number 2, which indicates that the address family is IP. So depending on the value in this field, the value in this field will be interpreted accordingly. So if this is 2, this means that this is an IP address. The IP address of what? This is the IP address of the destination network. So in the routing table, the important field for any routing entry, for any route entry, is what? The destination network, right? As we said, for any distant vector routing protocol, we need to indicate the distance and the direction. So the distance is the hop count or the metric. So what is the direction? So we don't have anything here that indicates the direction. The direction is simply the interface that this update came from. Okay? So when I send this update from, like for example, we have two routers like this. So this is router 1 and this is router 2. So router 2 sends route update. And this is interface like, let's say, F001 or something. Or whatever, S maybe. S001. So this route update, when router 1 receives it, if this route update, for example, contains destination address of 192. Let's say 168 or 167.4. whatever. Okay? And a hop count of, let's say, 2 or 3, whatever. The router 1 will put in the routing, based on this route entry, it will put in the routing table 192.168.4. 20.167.4.0. Okay, the distance is 2, and via F00 or S001, which is the interface that it came from. Which means that, sorry, the distance here will be 3, of course, because I have to increment, right? The distance here will be 3, and I know that it's 3 via this interface. So if I receive a packet and I want to send it to this destination network, I have to send it through this interface, okay? And it will go through a distance of 3 hops. That's what that means. So the direction is by default where this route update came from. That's why I don't have to communicate the direction explicitly as part of the route update. So in terms of operation, this is the command. So in the command, we have 2 possible messages for RIP. The first one is the request message, and we'll see how that works. And we have a response message. So if the command is 1, this means the request message. If the command is 2, this means the response message. So the request message, it gets sent out on startup. So one router every 30 seconds, it will send a request in a form of broadcast to ask all the routers around it to send it back the routing table information. Okay? The routers around it will send a response back which contains the response message, which will have the routing table information. So before we said that it's broadcast fashion, but here we say that it's based on two separate messages. One is the request and then response. And the request is broadcast, right? The response is unicast. The response is unicast. So the request enables the routers to send the routing information, which will be contained in the response. So IP addresses for RIP version 1 initially divided into classes. Because RIP version 1 is a classful routing protocol, it does not it does not send subnet mask as part of the route update. So the default is that the IP address will have an implicit subnet mask based on its class. And we know that how the classes are categorized. So class A indicates that you have the leftmost byte for network, and the rest is the host part, which means that the IP address in class A could be something like 120 or 90, let's say 90.0.0.0. This is class A. 96.0.0.0. We know that class A is all the IP addresses which has a leftmost bit as a 0, which means that you have 0, okay, and then anything in this byte, which means that you start from 0 all the way to 127, if the leftmost byte has any number from 0 to 127, this means it's class A. From 128 to كام؟ حد فاكر؟ 1 any IP address which has a leftmost byte that has 1 and then 0 and then anything else, this is class B. So if this bit is 1, this is class C. Okay, so from 128 all the way to 191 is class B. Okay, because 192 is 1, 1 and then anything else. Regardless, this is just to give you some examples how to recognize whether this IP address is class A or class B or class C. Of course, after 192 and after that is class C. Okay. So again, REP is a classful routing protocol, which means that it does not send subnet masks in the routing update. This is the accurate definition, because we will see in a minute that REP does deal with classless addresses, but it has to apply certain rules to know where this address, what is the subnet mask of this address. Okay, what is the subnet mask of this address? In a way which is different from sending the subnet mask explicitly as part of the route update, because it doesn't do that. It does not support sending subnet mask as part of the route update. So we talk about a simple example. So this simple example here talks about the fact that you have three routers: router 1, router 2, and router 3. Router 1 is connected to an Ethernet on an interface FA00, and it connects with router 2 through a serial interface. And what we can notice here is that all the network, the entire network, has an IP address which is in class C, which is 192.168.3.0 or .4.0 or .5.0 or .2.0. Okay? So all the network is homogeneous and it uses one class. Is in the same class, right? It's in each class, طبعا, we have multiple possible network addresses, right? So this is the basic configuration, and this means that we can construct this table easily. That router 1 has two interfaces. Has interface FA00, which has this IP address, and the subnet mask is this. The subnet mask here, this clearly indicates that in the routing table I store subnet mask. I do store subnet mask, right? But I don't send it as part of the route update. Remember that. Figuring out the subnet mask here is easy because all the IP addresses are classful IP addresses, and I have the entire network in the same class, so it's easy to realize or to recognize the subnet mask of each IP address. We will see another example that we use multiple classes in the same network in which case there is certain rule that you have to apply in order to calculate the subnet mask of an IP address without having to send it in the route update. Router 2 simply, of course, router 2, as you can see, has 3 different interfaces. 2 of them are serial interfaces, and 1 is an Ethernet interface, right? So this is what we have in the table: 2 serial interfaces, and again the IP addresses of each interface and the subnet mask, which is easily calculated because these are inherently classful addresses. So it's easy. So here we don't have any PCs attached to the LANs, and we use 5 different IP subnets. We use 1, 2, 3, 4, 5. Right? So we have 5 different subnets in that example. We have 3 routers set up, and each router has either 2 interfaces or 3 interfaces. And this means that the addressing table will look like this. And it's easy to calculate this subnet mask because all the IP addresses are inherently. So the basic configuration of rep 1, you have to specify the network. Of course, as part of this course, by the way, we're not going to go through the commands of how to configure routers and stuff, because this is not part of the course. What we are talking about here is the concepts. We're discussing here the concepts of routing protocols. So we're not going to go through these commands and what they mean exactly, but roughly you have to, for rep, first you start rep on each router, and then this command actually enables the interface to send route updates back and forth on this network. Okay, so this is roughly what that command means. So starting rep does not mean that you will enable the advertisement or you will enable the update to go back and forth by default. No, you have to enable the route updates to be sent back and forth on each network you are connected to. Okay, so this triggers the rep to send an update across these networks. Okay, and you have to do the same for all of them. So this is what's written here. So it enables rep on all interfaces that belong to this network, and it enables rep to advertise this network using rep route updates. Okay, so that's what this command means. So this is how you initiate the network. So you connect. Of course, you have to specify. Of course, you have to establish all these interfaces as you have studied in 455 before. You have to start the interface, configure all the IP addresses, and so on and so forth. And then you start rep, and you enable the route updates on each network that this router is connected to trigger the route updates to be broadcast. So that's what you have to do. A very important concept for rep is what we call automatic summarization. Automatic summarization talks about the fact that we don't necessarily have to maintain one route entry for each destination network. Okay? So until this moment, we've been talking about the fact that a routing table will contain one route entry for each destination network, right? Automatic summarization here talks about the fact it's a unified concept, which means that you can have one route entry for group of networks altogether. Okay? So for example here, in this example, we notice that the first thing we notice is that the IP addresses on this example, they have been modified. So it's not anymore 192.168. something. So we have 192 here, and we have 172 here. 172 is class A or B or C? B, right? So 172 is class B, and 192 is class C. So this network now has been is actually using multiple subnet addresses, multiple network addresses in two different classes. So it's not as homogeneous as the first example. So route summarization talks about the fact that router 2, if you notice, router 2 contains interfaces in two separate classes, right? صح ولا لا? So router 2 connects to some interfaces which are categorized in two different network classes. So these two interfaces are in class B, and this interface is class C. Okay? So automatic summarization talks about the fact that router 2 will be detected as a boundary router, because it's the boundary of two different subnetworks with two different classes. Okay? So first, router 2, we call it a boundary router. Okay? So router 2 uses a concept of automatic summarization, in which case you notice that the network on the left-hand side, this network, this whole network, our subnetwork, which contains multiple subnets, all these networks, they have the same class. And we can actually summarize all these networks using one simple address, which is 172.168.A.0.0. Remember that here we have multiple subnets. For example, we have 172.168.3.0 or .4.0 or .2.0. But router 2 running the rep protocol will be able to figure out that it can actually summarize all these networks using this address. And it happens that this address is a classful address, right? This address is a classful address. Because these addresses are using different, they use subnet which is not by default classful, right? Because /24 indicates class C, right? But 172 is in class B. So in general, this IP address is classless. This IP address is classless, right? Because it uses subnet mask. Okay? So rep uses the boundary router to summarize all these classes, all these subnet addresses into an address which is classful. So router 2 will send a route update to router 3 to tell it that if you want to go to any destination network in this region, you can use 172.168.0.0 and you can send it through this interface. So this means that router 2 summarizes all these subnets into this classful IP address. Okay? So that's what automatic summarization means. That I can group the IP addresses of multiple subnets into one classful address. And this is done automatically. Router 2 will do that automatically. That's why we call it a automatic summarization. Okay? So this is what's described here, is that the network contains, in general, 3 classful addresses. Okay? The first one is in class B, which is 172.30.0.0. Is it 30? I think it's once. Right. .30.0.0. This is class B. And we have 192.168.4.0, and these two are class C. 172.30.0.0 is subdivided into subnets. 1, 2, 3, and so on. And we can use these subnets on these networks here. Okay? And based on that, these networks, these subnets, can be summarized into a classful IP address at the boundary router. So we have to figure out where the boundary router is, and this boundary router will be able to summarize all these addresses, all these 3 addresses, into that address. Okay? So that's what automatic summarization means. Of course, automatic summarization leads to reduced size for the routing table, because I don't have to have a separate route entry for each destination network anymore. I can actually have one route entry to indicate multiple subnets, right? Which indicates that the size of the routing table will be reduced, which is a good feature. Because when the network grows very large, having one route entry for each destination network increases the size of the routing table. So automatic summarization is actually a useful mechanism which allows me to reduce it. But automatic summarization has to be done at the boundary routers. Okay? Okay, so we'll stop here.